urban power grids are reaching their physical limits. Data center clustering and electrification are driving unprecedented load growth in space-constrained metropolitan areas. High-temperature superconducting cables utilizing second-generation rare earth barium copper oxide tapes offer a high-density alternative. At a normalized 138 kilovolts, a triaxial superconducting cable transmits 1,000 megawatts of power. This matches the capacity of multiple conventional circuits while reducing the physical footprint by 64%. The resulting power density is 18.4 times higher than conventional copper cables. This spatial efficiency allows utilities to retrofit existing 100mm underground ducts. By avoiding new civil excavation, operators bypass the primary cost driver of urban grid expansion. Civil works typically account for 55 to 70% of total project expenditures. The primary bottleneck for superconducting transmission is not the physics of the cable, but the reliability of the cooling system. Superconductors require continuous cryogenic cooling at approximately 77 Kelvin. The mechanical refrigeration units, or cryocoolers, have historically exhibited low mean time between failures. Average cryocooler reliability has improved from 12,000 hours in 2015 to 44,000 hours in 2025. This progress narrows the gap to the 50,000-hour utility reliability threshold. However, any cooling failure triggers an instantaneous thermal quench. During a quench, the cable transitions to a highly resistive state within 50 milliseconds, risking catastrophic thermal damage. To mitigate this risk, 92% of active installations deploy redundant cooling configurations. This mechanical redundancy inflates initial cryogenic subsystem capital costs by 45 to 80%. The economics of superconducting grid projects are shifting. While the cost of the superconducting wire itself has declined by 33% since 2018, cryogenic cooling costs are rising. The cooling subsystem now accounts for 27% of total project capital expenditure. This cost inflation is driven by the integration of high-reliability helium and nitrogen compressors. Operational logistics also present a front-loaded hurdle. Initial cool-down protocols require up to 15,000 liters of liquid nitrogen per kilometer of cable to reach operating temperatures. Consequently, these systems remain restricted to high-density urban corridors. The high capital cost of cryogenic infrastructure is only justified where conventional right-of-way acquisition exceeds $15 million per kilometer. Cryogenic engineering, rather than material science, remains the gating factor for next-generation urban grids.